Hello everyone. In this video, we are going to see single phase semiconverter with RLE load. In RLE, in this single phase semiconverter with RLE load, we will have both continuous and discontinuous conduction mode. This will also give only one quadrant operation because of the inherent freewheeling action of the circuit. So let us first see the continuous conduction mode. In continuous conduction mode, the load current is always greater than 0. So I naught will be always more than 0. So we will not have any discontinuity in the load current. So here we can have the intervals, that is at alpha when we trigger, when T1 is triggered, when T1 is triggered, we will have the T1 and D1 combination. They are in on condition. This will happen from alpha to pi. From alpha to pi, T1 and D1 will be in on condition, which will result in the output voltage equal to Vs. So when T1 is in on condition, when T1 and D1, if they are in the on condition, the current flows through T1, through your RLE load, through T1 and back to the source. So V0 will be equal to Vs. So V0 will be equal to Vs when T1 and D1 are in on condition. This will be the case from alpha to pi. From pi to pi plus alpha, that is at pi plus alpha, we are going to trigger T2. So from pi to pi plus alpha, we will have the freewheeling action taking place. This freewheeling action will be taking place by the devices. Since T1 is already in conduction, T1 will conduct along with T2 because after pi, T2 is forward biased. So we will have the freewheeling action due to the conduction of T1 along with T2. So these two devices, they are now going to be in on condition. So when T1 and T2, they are in on condition, the load will be short circuited. So V0 will be equal to 0. Now at pi plus alpha, we are going to trigger at pi plus alpha, T2 is turned on. So when T2 is turned on, we will have from pi plus alpha to 2 pi, we will have the T2 and T2 conduction. We will have the conduction of T2 and T2. So this will result in the output voltage V0, which is going to follow minus Vs. Then from 2 pi to 2 pi plus alpha, again we will have the freewheeling action. This will be this action will be done by the conduction of already conducting thyristor SCR-T2 and T1. So when T2 and T1, when T2 and T1 are in on condition, again the load is being short circuited. So the V0 will be equal to 0. So this is the case. So these are all the intervals which will happen for one cycle. So initially when alpha to pi, during alpha to pi, when T1 and D1 are on, V0 will be equal to Vs. From pi to pi plus alpha, freewheeling action taking place, so V0 will be 0. From pi plus alpha to 2 pi, T2 and D2 are on, so V0 will be equal to minus Vs. 2 pi to 2 pi plus alpha, freewheeling action taking place, so V0 will be equal to 0. So if you we draw the V0, the V0 waveform will be from alpha to pi. The output voltage, it is going to follow the input voltage. From pi to pi plus alpha, we will have freewheeling action. So output voltage is 0. Then from pi plus alpha to 2 pi plus alpha, the output voltage will be equal to minus Vs. So during that time, Vs will be in the negative side. Since V0 is equal to minus Vs, that Vs is drawn in the positive side. So this is the output voltage waveform. And the output current waveform will be from alpha to pi. So the output current waveform will be from alpha to pi. So from alpha to pi, T1 and D1 combination are conducting. During the freewheeling action, we will have T1 and D2 conducting. During this pi plus alpha to 2 pi, we will have T2 and D2 are conducting. And before alpha, T2 and D1 combination will conduct. That is this during this period, 0 to alpha also, we will have the freewheeling action. Now, the current will be rising from alpha, from a non-zero value to this, and the current will reach again to the same value at pi plus alpha. So we will have the current which is rising from alpha, and the current will reach again to the same value at pi plus alpha. Then from pi plus alpha, again the current will rise from the same value, and it reaches equal to the same value again at 2 pi plus alpha. And similarly, before alpha, we will have the current. So from alpha to pi, the current will be carried by T1 and D1. From pi to pi plus alpha, current is carried by T1 and D2. And from pi plus alpha to 2 pi, from pi plus alpha to 2 pi, current will be carried by T2 and D2. And before alpha, the current is carried by T2 and D1. Now we can draw the source current waveform. The source current waveform will be equal to the load current waveform whenever the T1 and D1 combination are on. So we can draw the current waveform same as that of the load current waveform I0 whenever the devices T1 and D1 are in on condition. So this is the current when T1 and D1 are in on condition. When during the freewheeling action, the source current will be 0 because source is disconnected from the supply. During the freewheeling action, we have source current equal to 0. Then from pi plus alpha to 2 pi, whenever the T2 and D2 combination are on, we will have the current source current equal to minus I0. This current will be carried by T2 and D2. Again, from 2 pi to 2 pi plus alpha, during the freewheeling action, the input current will be 0. The same thing before alpha, the input current will be 0. So these are all the waveforms for continuous conduction mode. Now we can see that V0 waveform, it is similar to the waveform obtained for R and RLO. If you wish to see the derivation of V0 average and V0 RMS, you can have a look at the videos which is given in the description. So the V0 average will be equal to Vm by pi into 1 plus cos alpha. So which is the same value as we got for the R load and RL load continuous conduction mode. And the V0 RMS value will be equal to, since the waveform for V0 waveform is same as that of the R load waveform and also as that of the RL load waveform, V0 RMS value will also be same as that obtained for R and RL load waveform. So the expression will be, so V0 RMS value will be Vm by root of 2 pi into pi minus alpha plus sine 2 alpha by 2 whole to the power 1 by 2. This is the V naught RMS value. So these values, they are same as that of the single phase semiconverter with the R load and also with the RL load. So this is about the continuous conduction mode. Now we can see discontinuous conduction mode. In discontinuous conduction mode, we will have some period for which your output current will be 0. So we will have the I naught value will be equal to 0 for some time. Actually, at the time of triggering from alpha, the current I naught will rise and it will reach 0 at an angle beta, which is called as extinction angle. The value, that is I naught, will rise from 0 at alpha and it reaches 0 at beta. This beta is called as extinction angle. This will be that before we trigger the next device, before we trigger T2. So which means that beta is less than pi plus alpha. So because of that, we will have some we will have 0, I naught will be 0 for some time. So if we consider the output voltage for different intervals, we can divide the intervals into alpha to pi, then pi to beta, then beta to pi plus alpha, then from pi plus alpha to 2 pi, then 2 pi to pi plus beta to 2 pi plus alpha. So these are all the different intervals that we can have in the discontinuous conduction mode. From alpha to pi, T1 and D1 will be in on condition, which will give the V naught equal to Vs. V naught will follow the supply voltage waveform. From pi to beta, T1 and D2, they will be in on condition, which is freewheeling mode, which results in V naught equal to 0. Now from beta to pi plus alpha, no device will be in on condition. So all your T1, D1, T2, D2, they're all in the off condition. So which means that your load is disconnected from the source. So if we measure V naught, since the load is having E, we will have V naught is equal to E. Okay, V naught will follow the back EMF E. Then from pi plus alpha to 2 pi, T2 and D2 will be in on condition. So V naught will follow minus Vs. 2 pi to pi plus alpha, T2 and T1 will be in on, which is nothing but the freewheeling mode, which results in V naught equal to 0. Pi plus beta to 2 pi plus alpha, all the devices are in the off condition. T1, D1, T2, D2, all the devices will be in off condition. So results in V naught equal to E. Okay, so these are all the different intervals that are taking place, which will make V naught to follow different values during their different intervals because of the conduction of different devices. So if we draw the V naught voltage, output voltage, if we draw the output voltage, for one cycle, this is pi, this is 2 pi. We can divide the This is alpha, pi, and before pi plus alpha, we should have beta. Then after 2 pi, we will have pi plus beta. So from alpha to beta, from alpha to pi, we will have T1 and T1, they are in on condition. So from alpha to pi, T1 and T1, they are in on condition, which is at which the V0 will follow Vs waveform. From pi to beta, we will have the freewheeling action, which is a freewheeling mode, which during which T1 and D2 are in on condition. So output voltage will be 0. And from beta to pi plus alpha, we will not have any device in the on condition. So we will have the output voltage following back EMF E. Then from pi plus alpha to 2 pi, we will have the T2 and D2 combination conducting, which will make the output voltage to follow the minus Vs waveform. Then from 2 pi to pi plus beta, we will have the freewheeling action taking place due to the conduction of T2 and T1. So it will the output voltage will be 0. Then from pi plus beta to 2 pi plus alpha, we will have the output voltage following the back EMF. Similarly, before alpha, we will have we will have the output voltage, which is will have the output voltage following before alpha. We will have a freewheeling. We will have the no device on condition. So the output voltage will follow the input voltage. And here we will have the freewheeling action due to the conduction of T2 and T1. So this is the waveform for one full cycle. During this period, no device will be in the on condition. From alpha to pi, T1 and during this period, no device will be in on condition, at which output voltage is equal to E. From alpha to pi, T1 and D1 are on, which allows the V0 to follow Vs. From pi to beta, we will have the freewheeling action. So output voltage is 0. From beta to pi plus alpha, we will have the output voltage following back EMF. Then pi plus alpha to 2 pi, we will have the output voltage following minus Vs, because T2 and D2 combination are in conduction. Now the current waveform, I0 waveform, will be rising from alpha and it reaches 0 at beta. So current waveform will be having the shape like this. And again from pi plus alpha, the current will rise and it reaches 0 at 2 pi plus pi plus beta. So we will have the current waveform rising from pi plus alpha and it again reaches 0 at pi plus beta. Then before this, we will have the current. So this is from alpha to pi, the current will be carried by T1 and D1, then T1 and D2. Again from pi plus alpha to 2 pi, we will have the current carried by T2 and D2, and then by T2 and D1. And similarly here, the current will be carried by T1 and D1. V0 average will be equal to 2 by 2 pi integration from, we can split the integration into, since your output voltage waveform, it is equal to Vm sin omega t from alpha to pi, and then it is equal to 0 from pi to beta, and then it is equal to E from beta to pi plus alpha. So we can split the integration into 3 intervals. So which will be equal to 2 by 2 pi integration of Vm sin omega t. Sin omega t will be minus cos omega t. Limits varying from alpha to pi. Then we will have integration of omega t, which will be t. Which will be omega t, which limits varying from beta to pi plus alpha. So which will be equal to 1 by pi Vm minus cos pi, which is 1, plus cos alpha. Then from plus E, pi plus alpha minus beta. So this is the V naught average. That is V naught average, which is 1 by pi into Vm into 1 plus cos alpha plus E into pi plus alpha minus beta. This is the V naught average. Similarly, we can obtain V naught RMS, which will be equal to 2 by 2 pi integration from alpha to pi V naught square, that is V naught square, which will be equal to Vm square sin square omega t d omega t, and we will neglect the zero interval. Then we will have from beta to pi plus alpha, V naught square is E square d omega t whole to the power 1 by 2. Okay, whole to the power 1 by 2. Which will be equal to 1 by pi Vm square, we can take outside, integration 1 minus cos 2 omega t by 2 alpha to pi integration limit from plus E square, we can take outside beta to pi plus alpha d omega t whole to the power 1 by 2. So which is equal to 1 by pi Vm square by 2 we can take outside. Here d omega t should come. So integration of 1 will be omega t minus sin 2 omega t by 2. Limits from alpha to pi plus E square omega t beta to pi plus alpha whole to the power 1 by 2. So after integration and after substituting the limits, we will get V naught RMS equal to 1 by pi Vm square by 2 pi minus alpha plus sin 2 alpha by 2 plus E square into pi plus alpha minus beta whole to the power 1 by 2. Because when we substitute the upper limit, this term will be sin 2 pi by 2. Sin 2 pi is 0, so we have not considered that one. So this is the V naught RMS value. So V naught RMS value for single phase semiconverter with the RLE load in discontinuous conduction mode will be this one, which is 1 by pi Vm square by 2 pi minus alpha plus sin 2 alpha by 2 plus E square into pi plus alpha minus beta whole to the power 1 by 2. Thank you.